All right. So, hello. We're going to do T cells today. So, kind of continuing from B cells yesterday, we're at another adaptive immune cell. So, pretty much the same objectives as yesterday, but instead of talking about antibodies, we're going to be talking about like the subtypes of T cells and the different cytokines that T cells secrete. Okay, so some terminology before we kind of jump in. If I call something a naive T cell, you can also see this as T0, like a sub-zero. This just means it has never seen antigen before. It pretty much was made in either the bone marrow or the thymus and just now had left and gone into like the periphery and the secondary lymphoid tissue. That's a naive T cell. Um, Helper T cells are an overall class of T cell that has CD4 like has a marker called CD4 on its surface. So that's why I kind of said yesterday or whenever I talked about it very briefly, another name for a helper T cell or a T helper cell is a CD4 positive T cell. Every subtype of a helper T cell will have CD4 on its surface. So that's why they're called CD4 positive cells. All of the types have like TH in the name. It stands for like T helper. And then there's these different subtypes that we have to talk about. So there's a TH1, a TH2, TH17, Tregs, which I know isn't TH, but it's like a T regulatory cell, and then a follicular helper T cell. So this FH stands for follicular helper. Then we have cytotoxic T cells, and these are the other name for it is a T killer cell, and these have CD8 on its surface. So they're another name for these guys is CD8 positive T cells. And then we also have memory T cells. Okay, so these are all the different types of T cells. This is why I said it gets a little bit more complicated than B cells, because B cells, there's one B cell. And then there's like memory and effectors. There's the plasma cells, right? We have all these subtypes. So first we're going to talk about development. So as I mentioned, T cells mature in the thymus. That's where they get the name T cell because they come from the thymus. But remember that they're produced in the bone marrow and then they either go to the thymus and they finish their maturation there. The thymus can also produce some T cells, but remember the thymus involutes when you turn like 3 years old, by the time you're 3 years old. So they travel there and then they leave the thymus and then they go to like the secondary lymphoid organs. And that's where they would encounter antigen. So when it's leaving the thymus, that's like a naive T cell, a T sub-zero. The general process of T cell development kind of follows this scheme, and we're going to talk about that. It's kind of this whole, it's just like names in terms of the markers on the surface. So we have a stem cell, which is in the bone marrow, and now it's going to go mature in the thymus. So there's a series of double negative T cells, meaning there's no CD4 and CD8. So it's negative for both 4 and 8. That's what makes it double negative. Then it's going to turn into a double positive T cell. So it's going to have both CD4 and CD8. And then it'll turn into a single positive. So it'll either be CD4 positive or CD8 positive. That's your single positive T cell. So this is the general scheme: double negative, double positive, single positive. And we're going to go into details of that, but just kind of keep that in mind. So I kind of broke it up into like the steps of T cell development. So the first few are happening within the thymus. You can kind of think about this as like, but like the B cell receptor, when we went through like BDJ rearrangement, right, to test like the B cell receptor, that was happening in the bone marrow. So it's like this has to happen before it's even allowed to leave. So the first thing that you have to do is generate the T cell receptor, and then you have to test the T cell receptor. Again, it's kind of that same idea that we have to make sure it's not being autoreactive, right? It's not reacting with self-antigens. Then we go through positive selection, and then negative selection, and then migration to the secondary lymphoid organs. So again, kind of the general scheme of T cell development. So first we're going to talk about generation of the T cell receptor. So there's a concept known the race for rearrangement. This can get a little confusing, but I have like a summary kind of to explain what they're trying to, what they mean with this. So T cell receptors, I don't know why I said recall. I don't think I've ever told you this, but T cell receptors can either be alpha beta, meaning they have one alpha chain, one beta chain, or they can be gamma delta, meaning they have a gamma chain and a delta chain. When we're talking about like the normal T cell receptor, we're talking about the alpha beta chains. That's why that's the one that's drawn in first aid. That's the one that you should be thinking of when you're thinking of a T cell receptor. These are your traditional T cells. They're the ones that can recognize antigen. It's the T cell receptor. But there's another type of T cell that like T cell receptor that can be developed. It's called a gamma delta T cell, and it just means like one of the chains is made of a delta, like is a delta chain, and then the other chain is a gamma chain. The gamma delta, so I'll write like GD, the gamma delta T cell receptor is like not like a normal T cell receptor. It can't recognize antigen, like at all. It just basically is like a marker. It doesn't do anything. So there's like this idea of racing for rearrangement, because if the alpha beta T cell receptor rearranges first, that's the one that's going to win, and that's the type of receptor that the T cells are going to have. At the same time, the gamma delta chains are trying to rearrange. They're trying to win. So if the gamma deltas win, then we have T cells with gamma delta receptors that don't see antigens. So it's not terrible to have a bunch of not a bunch of these. It's not terrible to have like 1 or 2 T cells that have gamma delta chains, but you don't want all of your T cells having gamma delta chains. You'll never recognize antigen. And that's why it's almost as if like you have a T cell deficiency if you only have gamma delta T cells. So again, these TCRs are useless. TCRs is T cell receptor. These TCRs are completely useless when fighting an infection. So I'll kind of explain what this means. A lot of the time you're like, wow, that's terrifying. Like, what happens if gamma delta wins all the time? Like, this is usually not a problem at all, because like due to this concept of like, it's just probability that the alpha betas are going to win. And I'll show you what I mean by that on this slide. So here is our progenitor stem cell, right? So I told you it goes from the progenitor to double negative to double positive to single positive. So when we have our double negative T cell right here, we have our first race. We have our first race for rearrangement. And basically it's going to be the beta chain versus both gamma and delta. So we have one chain trying to rearrange versus 2. That's why it's like the sheer probability beta is going to win, just because it's 1 versus 2. Again, it's not impossible that gamma and delta rearrange before B, but just keep in mind, like the sheer probability is it's like it's kind of like for the B, like you're rooting for the beta chain rearrangement. Okay. So let's say though gamma delta wins, fine. Now we have a committed gamma delta T cell. It's done. Like this is it. This like it's kind of a useless T cell, but that's what happens. If beta wins, which is what happens the majority of the time, now we kind of move on to that next step. So now we have our double positive T cell. And from here, now we need the alpha chain to rearrange. And it's the same concept. It's the alpha chain gets to rearrange versus the gamma and delta again. It's like the gamma delta gets a second chance to try and rearrange. So again, sheer probability, alpha is going to win. We're going to have our normal single positive T cell with an alpha beta T cell receptor on it. But if gamma delta wins, not a big deal. We just have a gamma delta T cell. We don't want it happening again all the time, but if it happens every now and then, it's really not a big deal. But when they're talking about the race for rearrangement, this is what they're talking about. We kind of want the T cell receptor to be alpha beta, and it races against the gamma delta receptor trying to develop. Okay. So when the B cell, I kind of put this on here because when the when the beta chain is rearranging, so back here, when this beta chain is rearranging, it can't just rearrange by itself. It needs a surrogate alpha chain. So it needs a surrogate, kind of like remember when the heavy chains, when we talked about the heavy chain rearrangement after it underwent VDJ, then the light chains needed to rearrange. You needed to add surrogate light chains. It's kind of the same idea. So if we want the beta chain to rearrange, we need to kind of add like a surrogate alpha chain. It's the same thing. It's like a fake alpha chain. It's called PT alpha. I remembered it as it's like the pre-T, like the pre-T cell receptor, like the pre-alpha one. So that's what this is. And it's just basically allowing the beta chain to completely, it's allowing the beta chain to be able to fully rearrange versus gamma delta. And then eventually the alpha chain will rearrange and then take over its spot. But I mention it because if you have a deficiency in this, so we have a deficiency in PT alpha, beta can't completely rearrange. The alpha chain can't really get put on there. You're going to have an increase in gamma delta T cells. So if you have more gamma delta T cells, that means you have less alpha beta T cells. You're not recognizing antigen as well, and it can kind of present as like an immunodeficiency. So that's kind of what this race for rearrangement is. So if you see that on slides moving forward, here's race 1, here's race 2, that's what I'm talking about. It's kind of like the B cell receptor has to win, and then the beta chain has to win, and then the alpha chain has to win in order to get your actual T cell receptor that we all know and love. Okay, does this make sense? I hope it makes sense. But yeah, that's all oh my God, PT alpha is. It's like the surrogate light chain. Okay, so T cell receptor subtypes. So, like I mentioned, we are in favor of alpha beta lineage. It's always going to be 1 versus 2. It's always going to be beta versus gamma delta, alpha versus gamma delta. But gamma and the gamma delta rearrangements occur at these 2 different stages. It's basically like I said, like you get like 2 chances. Like, hey, are you sure you don't want to make a gamma delta? Maybe like you want to make one today, maybe. So it's going to happen once when the T cell is double negative, and then once when the T cell is double positive. So if I go back here, here's kind of the first race. So gamma delta gets to try and rearrange when it's double negative. The second one is back here when it's a double positive cell. And we're going to go more into detail about like double negative, double positive. Once alpha chain occurs successfully, you can no longer produce a gamma delta T cell. So that's kind of why it's like the body's way of being like, hey, you have 2 chances and that's it. You don't get a 3rd chance. And again, I really just want to emphasize gamma delta T cells are not like normal T cells. Like, I really don't want you to think like you see gamma delta T cell, be like, oh, well, it's still a T cell. No, it like it is, but like it's not. It doesn't even undergo positive selection. It doesn't undergo negative selection. You can kind of see why this would be an issue if you just let the cell go out into the periphery, and it doesn't recognize peptides. So it really can't, it doesn't really do anything. It does have functions, but you don't have to know it. You don't have to know like what they actually do. They kind of act like innate cells. But you don't have to know it. Just kind of understand like this race is happening, like to get like the proper alpha beta receptor. Okay, so you have to know where these selection processes are occurring. So I mean, like, where do you have double negative? Where do you have double negative T cells? Where's positive selection? Where do you have double positive T cells? Where's negative selection? Kind of know that, and then going a step further, be able to identify it on like a histo slide. So remember, we kind of talked about like the thymus back on like day 1. Like the cortex is going to be on the outside. This is more of like a traditional cortex medulla setup. So the cortex is going to be on the outside. The medulla is going to be closer to the middle. And remember, the medulla has these weird Hassel's corpuscles in the middle of them. And that's how you can identify the medulla. And again, I'll emphasize this. So I'll be like, definitely know like this is happening in the cortex. This is in the medulla. I'll emphasize it. So like I said, double negative, double positive, it's just like a way to kind of understand like how mature your T cell is. So for example, a double negative T cell, this is like a T cell that has just left it has just left the bone marrow and it like just got to the thymus. Or if it is produced in the thymus, it like just was produced. It hasn't undergone any maturation yet. So double negative means it doesn't have any CD4 on its surface. It has no CD8 on its surface. So this is another way that they could write a double negative. They could write this T cell is CD4 negative, CD8 negative. This just collectively, this means it's double negative. Double positive means it has both CD4 and CD8 on its surface. So this is another way that they could write double positive, CD4 positive, CD8 positive. And then I put this here, CD3, because all T cells have CD3 on their surface. It's kind of like yesterday I put like MHC1 on the B cell to remind you guys like, yeah, B cell's an antigen presenting cell. It's going to have MHC2, but don't forget it also has MHC1. Kind of the same thing here. Like it's going to have CD3 on its surface as well because every single, like this is like a marker that tells you like this is a T cell. It has CD3 on its surface. Because you can't ask the cell, hey, what type of cell are you? You can't ask it that. So it's kind of like if you're like if you're screening cells, you're like, oh, this has CD3, it has to be a T cell. That's like the lineage it comes from. Okay, so back to like this generation of the receptor. So I think this is there's a lot going on here, and I know I added some more stuff, but it's a really good kind of visual to keep in your mind. So let's say like this. So let's say these are coming in from the bone marrow. So let's say that these T cells, oh my God, were produced in the bone marrow. And now it's coming to the thymus to finish its maturation. So they're coming in. They're going to come in through a venule. They're coming in, and now they're double negative when they enter, right? So they're coming in, they're double negative, they haven't done anything yet. The first race for rearrangement occurs. So now it's either like, all right, are we becoming a gamma delta T cell, or are we rearranging the beta chain successfully? More likely than not, actually mostly all the time, you rearrange the beta chains. And now it's like that checkpoint. Remember I said like yesterday too, when you have like the heavy chain rearrangement, the surrogate light chain is kind of like a checkpoint to make sure like, yeah, the heavy chain was rearranged correctly. It's kind of the same idea as putting like the surrogate alpha chain on there. It's like a checkpoint to make sure like, okay, the beta chain rearranged correctly, we can continue. So that's what they mean by checkpoint. So this is like your PT alpha surrogate chain gets added here. So now it's going to keep going, and now we're going to have a double positive T cell. So double positive cells here. Then we have our race for rearrangement 2. So our race for rearrangement 2 is now the alpha chain needs to rearrange, or we give the gamma deltas a second chance. So that happens, and a lot of the times the alpha chain's going to win. It's going to win the race, and we're going to end up with mature double positive T cells at the end of this. And mature meaning they have an alpha chain and a beta chain on its T cell receptor, like making up its T cell receptor. This is not selection. We haven't talked about positive and negative selection yet, so don't get confused with the positive and double positive and negative and double negative. This has nothing to do yet with negative and positive selection. This is just generating the T cell receptor. This is something I also tried to do to kind of show you guys, like if we go back, well, not go back, but just very quickly, when I'm talking about like, this is the general outline, I tried to put in the top left what stage we're talking about, just so you don't get confused. So positive, negative selection are down here. So again, just keep that in mind. So we're still generating the T cell receptor at this point. Okay, so from here, we have this mature double positive T cell. What makes the cell become double positive? And this is the pre-T cell receptor proliferation. So as soon as you have this right here, as soon as we have this pre-T cell basically putting on the surrogate alpha chain to the beta chain and allowing it to proliferate, again, this kind of mimics B cell development, right? That's the type of B cell that proliferates. It's the one with the heavy chain completely rearranged and then the surrogate light chain. That's the one that's allowed to proliferate. Same thing here. The beta chain is completely rearranged and we have the surrogate alpha chain. This is allowed to proliferate, and this is kind of like the signal to become double positive. So that's a signal for the cell to now go back and express both CD4 and CD8 on its surface. So then after the alpha chain completely rearranges and it beats gamma delta, then we're going to have a double positive alpha beta T cell. Okay. So that's TCR generation. So now we're going to kind of go through this process of positive negative selection, which is basically just testing the T cell receptor. So we kind of need to make sure that the T cell receptor doesn't interact with self antigen. We have to go through this whole process, just like we did with the B cell testing positive negative selection. So we're going to test it now. So first what happens is negative selection. So negative selection is happening in the cortex. You need to know that. Need to know. Absolutely need to know. Have I mentioned you need to know this? Okay. You need to know negative selection happens in the cortex. And to kind of help, that's why, again, I use this figure a lot because I think it just has everything you need to know. But these cells here are cortical epithelial cells. And again, cortical epithelial cells, they're in the cortex. So that's kind of a reminder, like they're going to obviously play a role with negative selection, but they're going to be the name tells you, like that's where it's happening. So I kind of took this and transposed it because I think that this is too hard to explain on here. So this is the same cell. I tried to keep it the same color. So this is a cortical epithelial cell. Okay, so we're in the cortex. And what the cortical epithelial cell does is it expresses self-antigen with both MHC1 and MHC2. So again, before I continue, remember the rule of 8. MHC1 is going to interact with your CD8 positive T cells. 1 times 8 is 8. And MHC2 is going to interact with your CD4 positive T cells. 4 times 2 is 8, right? So just as a reminder. So these cortical epithelial cells, they have both MHC1 and MHC2 on their surface, and they load it with self-peptide. So this is, okay, so then this is what happens here. So this is your mature double positive T cell. It's going to interact with the cortical epithelial cell. And basically, whatever one it's reacting to better is the one that survives. So the whole idea of positive selection, make sure the T cell receptor can recognize and moderately strongly bind to MHC. This is kind of different. Actually, do I have it on here? Yes, I do. This is very different from B cell receptor selection. So remember how I said that T cells can only see antigen in the context of MHC? Technically, MHC is self-antigen. It's technically your self, like your body, right? They're found on every single organ in your body or your antigen-presenting cells. So you still need the T cell to kind of recognize it. So positive selection is like you want the T cell to recognize this self-antigen, meaning the MHC. So what's weird here is you're seeing like weak or no binding to self-antigen. Again, super weird. It's going to die. If it binds moderately or strongly, it's going to live. And this is positive selection. Did I say negative selection back here? I think I did. Oh my goodness. Wow, that's not good. All right, guys, positive is in the cortex. Oh my goodness. Positive happens first. It happens in the cortex. I'm so sorry. I will change that on the PowerPoint before I send it out. Okay, so it's kind of weird, kind of confusing, but stay with me. Stay with me. So this is very, very different from it. Oh yes, this meme. So remember, T cell receptors can only see antigen in the context of MHC. So remember, like, if we have a T cell here, it can't see what this macrophage or whatever is presenting to it if it doesn't have the antigen loaded on an MHC molecule. Conversely, like phagocytes, they can just eat whatever. They don't need to see antigen in the context of MHC. B cells don't need to see antigens in the context of MHC. They don't need to. They can gobble it up, right? Or B cells can get cross-linked with the receptors. But T cells, this is a huge, huge concept, and this is why positive selection exists. We kind of need to positively select for T cells that at least kind of recognize MHC. Okay, and then this was back from that lecture on Tuesday. So I tried to emphasize it a little bit here, saying like the T cell isn't just recognizing antigen, it's also recognizing MHC. So positive selection is making sure the T cell receptor can recognize MHC. And don't worry, like I know some people are like, well, isn't it bad if it's recognizing self-antigen? It's fine for now because we have negative selection. That's why positive happens first. That's why I was like, oof, no, it's like the cortex. It's happening first because we at least want to make, like, if this is binding to this, that means clearly it's recognizing MHC because it can only see antigen in the context of MHC. So yes, it is binding to self-antigen, but we don't have to, like, don't worry about that right now. It's like, we got bigger problems right now. We have to just make sure we see MHC first. So that's why this is going to live. Again, weird concept. It's like very different from B cell stuff. So here's like your summary of positive selection. So here's your mature double positive T cell. It just underwent alpha beta chain rearrangement. This just kind of went through that process. So it's a mature, it's double positive. Okay. So if the T cell receptor binds weakly to the self-antigen within MHC1 or MHC2 presented by the cortical epithelial cell, if it's going to bind weakly, it's going to die. Okay? And this is kind of that whole idea we talked about. Like, this is not negative selection, like death. It's not negative. It's just not positive. It's the same idea as like the B cell stuff. Like selection requires like you're actively doing this. This is just if it binds weakly or it doesn't bind at all, it just automatically dies. The default pathway is death. But back here, if it's binding moderately or even strongly, and again, super weird, but even if it's binding strongly to the self-antigen within the MHC1 or 2 presented by that cortical epithelial cell, again, we're in the cortex, now we're actively selecting for it. We're positively selecting. We're like, yes, we want you. So we're selecting for it. It's going to survive, and now it's going to continue on to the medulla. Okay, so we have this mature double positive T cell that's able to move on to the medulla. Okay, so that's positive selection. Negative selection happens in the medulla. There we go. That's not a typo. Yes. So negative selection happens in the medulla. And so here's our mature double positive T cell that just got positively selected for. And here is your either a medullary dendritic cell, a medullary epithelial cell, or a medullary macrophage. And remember I said yesterday we talked about air like very briefly, and I'm like, we'll talk about air like tomorrow. Here's air. And air is just a gene. These medullary cells have air, and air is what kind of is what allows this process of negative selection, which you'll see in a second. Okay, so these medullary cells, they look exactly like the cortical epithelial cells, but now they have both MHC1 and MHC2 on its surface, loaded with self-antigen, and they're going to be air positive. Okay, so here's like an air positive dendritic cell, so we know like this is a medullary dendritic cell. And now at this point, we want to make sure that the TCR receptor can bind moderately to self-peptides presented by air and to delete cells that bind too tightly. So again, it's this concept of if it's binding tightly here, again, it's MHC presenting self-antigen. This is going to die. Moderate binding, it's going to live. And at this point, we don't want it to not like we don't want weak binding here, because again, if you have weak binding, it probably is not recognizing MHC. It's probably one of those ones that kind of like escaped positive selection. So we want moderate binding for negative selection. And we'll keep talking about it, but just briefly on AIR. So AIR, it stands for autoimmune regulator. So autoimmune regulator. Thymic medullary cells, dendritic cells, epithelial cells, whatever, just these medullary cells express self-antigen transcribed by this AIR gene. And I say, like, think of AIR as being the gene that allows medullary cells to be, like, even have the ability to express so many different self-antigens. Okay? And here's a little bit more on AIR, but you don't have to know the specifics of like gene mutations. It's just like AIR is a gene, right? So it's a gene, it can be mutated. So here's a normal thymic medullary cell. It has normal AIR gene activity. So this is like AIR positive. It's able to basically show the T cell this vast, beautifully colored repertoire of self-antigens. So it can show some maybe from the liver, show some from the spleen, show some from the, I don't know, I forget organs. Just it can show like all of these different antigens from all the different organs in the body. And it's a really, we want a really vast repertoire being shown to the T cell. But let's say we have a mutation in AIR. So AIR got mutated in some way. Maybe it got knocked out completely. This is just, it's not able to do that anymore. So we have like this very limited repertoire of self-antigen. Maybe it can only show skin antigen, and that's it. Or like skin and like maybe a little bit of something else. That's kind of why it's really bad to have these AIR mutations, because you can't show the T cell all of the potential self-antigens that it could come in contact when it's going around in the periphery. So AIR gene mutations present as a disease state, which I don't think we talk about in the immunodeficiency lecture. I don't think we do. But just keep in mind, it's called autoimmune polyendocrine syndrome. Autoimmune polyendocrine. And again, it's polyendocrine. We're going to have a lot of endocrine issues because for whatever reason, it's just not able to show endocrine organs, but that's fine. It just can't show these different like antigens from these different endocrine organs, most commonly with AIR mutations. So again, AIR is really important for negative selection. If AIR is knocked out, we're going to have autoreactive T cells that are going to, for whatever reason, in autoimmune polyendocrine syndrome, react with all the different types of endocrine organs. So you can imagine how vast the symptoms would be here. Oops. Okay, so that's AIR. T cells autoreactive, they start attacking the endocrine organs. Okay, so now the T cells, let's say we have a T cell that has passed positive selection, it passed negative selection. Now they're going to become a single positive T cell. So here's our double positive T cell. Receptor binds to self-peptide and self-MHC class 1. If it binds, and I think I go into this a little bit more. Yeah, I do. It depends on which MHC it's reacting with more closely, like better. I have to be careful. It's not like which one it's interacting with more. It's just like better, because you actually don't want it to, it's moderate binding, right? So it's like which one it's binding to more moderately, that's the type of T cell it's going to develop. So if it's reacting really nicely with like a CD8, with the CD8 positive like marker, then it's going to turn into a CD8 T cell. If it reacts, if it reacts really nicely with MHC class 1, it's going to turn into a CD8 positive T cell. And then CD4 is out here like in the dust. If it reacts really nicely with an MHC class 2, then it's going to turn into a CD4 positive T cell. So this is what's meant by single positive. Now it's either 8 or 4. And again, a CD8 positive T cell is a cytotoxic T cell. CD4 positive T cell is a helper T cell. Okay, so let's say this is a mature double positive T cell that passed both positive and negative selection. And now we need it to turn into a single positive T cell. So during that process of negative selection, it still passed, but during that process, which one is it reacting? Maybe stronger is not the best word, better. The T cell receptor, which one is it interacting better with? If it's MHC class 2, it's going to turn into a CD4 positive T cell, MHC class 1, CD8. And this is like another way that they could describe, this is another way they could write it. So a single positive T cell that reacted better with MHC class 2 would be 4 positive, 8 negative. And if it's a T cell that reacted better with MHC class 1, it'll be CD4 negative, CD8 positive. Okay. So summary of negative selection happens in the medulla. So the mature double positive T cell, it passed positive selection. Again, with positive selection, we want it to bind self-antigen presented by MHC class 1 or 2 moderately or strongly in the cortex. So once it passed positive, it goes to negative. So then from here, let's say the T cell receptor binds really super strongly to MHC class 1 or class 2, which is presented by an AIR positive medullary cell of some sort. Too strong, it's going to die. Let's say the T cell receptor binds moderately to MHC class 1 or 2, presented by the AIR positive medullary cell, blah, 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 then it'll survive. This is the selection process. I don't want to put a plus, but this is negative selection, but this is the selection process. And then if it reacted better with MHC class 2, it's going to turn into a single positive CD4 T cell. If it reacted better with MHC class 1, it's going to turn into a CD8 positive T cell. And then overall summary of everything we just talked about. So first, generate your T cell receptor. So your beta chain is going to rearrange first, and that's going to go against gamma delta. This is your double negative T cell. This is race for rearrangement 1. Then you couple the surrogate alpha chain, so pre-T alpha, you couple that to the beta chain. That's going to proliferate. That signals the trigger for switching to double positive, and then the alpha chain is going to start to rearrange against, it's going to try and fight, like go against gamma delta. This is your second race for rearrangement. It's most likely going to win. And so we have a mature T cell receptor on a double positive T cell. So we have an alpha beta T cell receptor on a double positive T cell. Now we have to test it. So we want to make sure it's can recognize self-antigen, but also not too much. So the first one is we want to recognize MHC 1 or 2 with moderate or strong binding affinity. Again, we're in the cortex. This is cortical epithelial cells. If we do this, it's positively selected for. If it does recognize MHC weakly or just not at all, it's going to die. And it's, again, this is a passive process. The default is death. The second goal is we want to recognize self-antigens presented by those AIR positive cells, again, in the medulla with moderate affinity. If it does this, it's going to continue on to be CD4 positive or CD8 positive. That would be like a single positive cell, depending on which one it's interacting with better. But overall, if it's too strong, it is negatively selected for. That is a negative, like we're selecting for it to not continue. Okay. This is your summary. Okay. So then looking at this process, just now you can kind of like follow along with what's going on in this image. We have a CD3 negative. So again, this is like our very first cell that we created. It's CD3 negative. It doesn't even have the T cell marker on it yet. So it's CD3 negative, CD4 negative, CD8 negative. These are your double negative cells, but they're also CD3 negative. But when they're talking about double negative, they're talking about 4 negative and 8 negative. From here, we have race 1. And remember, this is kind of where they pick up. This is like kind of where it picks up the CD3 positive thing. So that tells it it's a T cell. But race 1, beta chain can either rearrange or the gamma delta chain can either rearrange. From here, there's race 2. It's not shown. From here, there's a second, like the race for rearrangement 2, not shown. But at the end of that, we have alpha and beta positive. It's the trigger to switch over to 4 and 8, like double positivity. And then from here, we undergo positive selection in the cortex, negative selection in the medulla. And then we have, depending on which MHC they react with better, it's going to turn into a single positive cell. Remember, this is another way you could write it. And then it's able to leave. And I wanted to note how many T cells are actually passing this process. Most of the T cells die. So most of the T cells are self-reactive. Again, you can imagine why this is such an issue. Like why, like if this process is not highly regulated, that's kind of where they think autoimmunity is triggered from. What exactly triggers its change to double positive? I'm not exactly sure, but I know it's when what is it? The surrogate chain. When the surrogate alpha chain, I don't know why I went back one by one. When the surrogate alpha, so the pre-T like alpha chain is like added to the B cell, oh my God, I keep saying B cell. The beta chain has the surrogate alpha chain added to it. When that's there and now it's able to start proliferating, that's a signal. I don't exactly know what the exact signal is. It's probably some signal transduction pathway that just tells like the cell to transcribe both CD4 and CD8. But it's basically like right here. like right at this point is when you get the double positivity. So after this proliferation step. Yeah, no problem. All right, I won't go back one by one. But yeah, so only less than 5% actually make it out of here. So positive selection and negative selection is a pretty intense process. And then back to these ideas of central and peripheral tolerance. So when we're talking about central tolerance, again, central, think your primary organs. So central tolerance with T cell development is going to be in the thymus. So that they're talking about positive selection in the cortex and negative selection in the medulla. Whereas peripheral tolerance, we'll talk about we'll talk about when we talk about activation. That's going to be once the T cell leaves and now it's in the periphery. It's in like those secondary lymphoid organs. That's going to be where peripheral tolerance kicks in. Okay, so the immature single positive T cell leaves the thymus. This is probably your T sub 0. It's a naive T cell. How does it know where to go? Chemokines. And again, I remember I told you guys you don't really have to know these chemokines. I think that was something that Dr. Demarest last year wanted them to know. They're really not that important. Like they're a low yield chemokine, I should say. But just keep in mind, like now we kind of want cells that are going to draw it to the secondary lymphoid tissue. So we have things like that are going to attract T cells to the high endothelial venules. We have like dendritic cells, which are antigen presenting cells that are secreting things to attract T cells to where they are. And then this is a receptor, but this is what's on the T cell. You don't have to know it, but yeah, just keep in mind, like there's these chemokines that are kind of telling this immature T cell, the immature T cell that just left the thymus where to go. Okay. So next we're going to kind of dive into like peripheral tolerance and T cell activation and differentiation. And this is kind of what I meant when we're talking about how like T cells can only see antigen in the context of MHC. Nice little meme there. Okay, so we talked about T cell development right here. This is up to in first aid what we just covered. So positive selections in the cortex, negative selections in the medulla, and it goes from a double positive T cell to a single positive T cell during this process. And then this would be a double negative T cell. So this is what we're going to talk about next. And this is where I said like T cell stuff gets a little bit more confusing than B cell stuff because there's all these different subtypes of like T helper cells. And you have to know some of these cytokines and some of these functions, like when they become important. But we're going to talk about activation of a T cell first. So just like B cell activation, T cell activation requires two signals. It's the two signal hypothesis. This is really the body's way to make sure that you really want to activate the T cell. Like you didn't just accidentally activate it. Like we really do want to activate it. So the activation signal is pretty much going to be the same as in B cell activation. So it's either going to be the T cell receptor binding to an MHC class 2 or an MHC class 1. So that's this interaction. So TCR to MHC 1 or 2. And then depending on if it's MHC class 1, it's the TCR plus CD8. And it's if it's interacting with MHC class 2, it would be the TCR plus CD4. Because you can see here, it's like both are binding to the MHC. And then the co-stimulatory signal for T cell activation, we kind of briefly talked about this yesterday with like one of those questions we did at the end. The co-stimulatory signal here is going to be B7 and CD28. And you have to know which one's on which. CD28. So B7 is going to be on your antigen presenting cell. So in this instance, it's a dendritic cell, but B7 is usually on your APC. And then CD28 is going to be on your T cell. And again, remember your co-stimulatory signal is your survival signal. This is like the signal that tells it like, yeah, we wanted you to be activated. And then if we're activating T helper cells, so if this was a CD8 positive T cell, like a killer T cell, once signal 1 and signal 2 happen, the CD8 positive T cell can kill its target. But let's say this is a T helper cell, which is what it's showing here in this picture. So if it's a T helper cell, there's the signal 3. And remember signal 3 yesterday, which is the cytokines, which tell the B cell like, hey, I need this antibody, I need this antibody. Signal 3 here tells the helper T cell which type of helper T cell to be. So if we go back a slide, you can see there's all these different types of helper T cells that it can turn into. So depending on which cytokines it gets, tells it which type of helper T cell it like needs it to become. Is signal 2 the same regardless? Yeah, good question. Yes, same signal. It's always going to be B7 and CD28. And remember, co-stimulatory signals as well, they're only expressed when the cell has, when there's an infection. That's kind of like the way to make sure that you actually want to stimulate the T cell. Like the APCs only upregulate B7 when there's an infection. This, I don't think you guys have this slide. I added this in because one of my friends that took STEP like last week or 2 weeks ago said that there's a CTLA4 question. I asked him like, hey, like what immuno do you guys have on there? I don't think you guys have this, but if you don't like frantically write notes. It'll be in the PowerPoint when I upload it later or send it to Sarah. But I wanted to mention it because this was on her boards, so we're going to talk about it here. So CTLA4 stands for cytotoxic T lymphocyte associated protein 4. Everyone just calls it CTLA4. So why I put it right after like where we talked about these signals is because CTLA4 blocks this interaction of B7 to CD28. Oh, you did get a URL question on this. Yeah, see? Yeah, so they love CTLA4. So, well, this year it seems like they do. So B7 and CD28 normally bind. This is your second signal, right? So here would be signal 1, here would be signal 2. CTLA4 binds to B7 and it's like, nope, no signal 2. We don't need signal 2. There's no infection. We don't need it. That's what this does. So CTLA4 blocks co-stimulation so we don't get T cell activation. I also wrote CD80 on here because this is immunology, right? They lose their audience. Right here, CD80 is another name for B7. It's really annoying. So if you're doing questions and you see CD80, I know it's really annoying, but that's another name for B7. So if you can, whenever you see B7 or CD80, just write them next to each other. So you just kind of like get in the habit of seeing these two as being the same thing. I always think of it as like there's probably 2 immunologists that are like arguing. Someone's like, they all have to be CD something. The other one's like, no, they don't. But yeah, so this is their compromise. But anyway, so B7 or CD80 binds CD28. CTLA4 blocks that so that we don't get co-stimulation. This T cell will not get activated. Okay, and this is not a bad thing. This can be done physiologically, like I wrote here. Like if there's not an infection, we really don't want T cells to get activated accidentally. So it's kind of like a way to keep the T cell in check. But where there's smart processes in place like this, cancer cells can kind of hijack them for their own good. So the cancer cells can also be like, ooh, okay, so let me just upregulate CTLA4 and then we will never get a T cell being activated. So cancer cells can actually put CTLA4 on their own surface, or they can trick T cells to upregulate CTLA4 so that they can basically hide from the T cells. And we're going to talk about this more in the last lecture, like how does cancer like hijack parts of the immune system to kind of like hide from it. And I also want to mention it because there's a really big farm drug that is like really good recently, and it's blocking CTLA4. It's called ipilimumab. You guys don't have to know this for your exam. It's more of like a boards relevant thing, like a fun fact, that this is like a brand new monoclonal antibody that like Big Pharma developed that blocks CTLA4. So if for whatever reason they think this cancer cell is upregulating CTLA4, they can give this monoclonal antibody to block it so that B7 or CD80 can bind to CD28 and we get T cell activation. So it's like, hey, go find the cancer. You're activated, go find the cancer. So that's just like a fun way to kind of like use drugs to kind of play off of the immune system. It's really fun, I promise. Okay, so here's your CD8 and CD4 activation. They're going to be the same process. It's just going to depend on is it MHC class 1 or class 2, and is it the CD4 or CD8 that's binding to it. So here's your T sub-0, your naive T cell. It has one of those on the surface, not both, and it just depends on which MHC it's interacting with. So if it's interacting with MHC class 1, it's going to be CD8, and then class 2, it's going to be CD4. So that's signal 1. And then signal 2, oh yeah, CD80, 86 as well. All right, so CD80, 86, which is B7, and CD28. These are going to interact. Again, this is only upregulated when there's an infection. It probably has something to do with when it processes antigen and it's going to put it on its surface. It probably triggers it to upregulate this co-stimulatory signal. And then from here, there would be like the release of cytokines to kind of tell this T cell what type of T cell to turn into. Okay, so specifically CD8 activation. So CD8 positive T cells and CD4 positive T cells are a little different. So CD8 positive T cells, they're kind of always patrolling around the body. I think of these as like the police officers of like the body. They really are just kind of always patrolling, and they're trying to make sure that every single cell has its MHC1 on its surface, right? And it's going to come along and it sees here, oh, here's a different type of antigen within this cell, and here's a co-stimulatory signal. Oh, okay, so it's going to come here and it's going to get activated. So it's going to come over, it's going to bind to it, it's going to bind to it, and then we get signal 1, signal 2, and then from here, the T cell is going to become activated. Again, this is CD8 only. It's going to release IL-2, and it's going to release interferon gamma. So IL-2 is for itself. Remember hot T-bone steak. This is T in hot T-bone steak. This is T cell growth factor. So it's actually kind of cool. The T cell's releasing its own cytokine to stimulate itself to like grow more. Insane. But then it secretes interferon gamma, and interferon gamma basically is what allows this cell to like die, basically. So it's going to secrete interferon gamma. It like preps the cell for death, and then it's going to release porphyrin and granzyme. And these are the two things that actually cause death within the cell. Note here as well, these are also the exact same like things secreted by an NK cell. So if this was an NK cell and this did not have MHC on its surface, the NK cell would be like, all right, I need to kill this. So it would secrete porphyrin and granzyme as well. And again, NK cells, they're of T cell lineage, so that should make sense. NK cells are literally the CD8 positive T cells of the innate immune system. Okay, so that makes sense. So that's the first thing that happens. Release of IL-2, release of interferon gamma. How do you know if it's going to be an NK cell or a T cell? Like, do you mean looking at it in the peripheral blood? Because if you're just looking in the peripheral blood and you see like a lymphoblast, you can't tell if that's an NK cell or a T cell. You have no idea. But T cells need to be activated. So you need to like actively activate T cells. NK cells are always also just kind of patrolling around. They're also patrolling around. They're looking to make sure that a cell doesn't have MHC on its surface. And then they would get activated to kill that cell. I don't know if that's what you were asking, but you can okay. We'll talk about it more if you're still confused. Okay. So this is this. Okay, and then once that happens, what's really cool about CD8 positive T cells is that it's a very specific process. Like it literally only kills this one cell. It doesn't cause any other cells in the little sheet to get affected. It's only the cells that are up like putting that viral antigen on its surface. Fun fact, type 1 diabetes is literally this process. So type 1 diabetes is literally like the cells think that there's self-antigen and it presents it, the pancreatic beta cells. They literally think that there's a infection or something. It presents self-antigen, and that's why the T cell comes in and it starts to destroy the cells. But it's the exact same process with type 1 diabetes. It's just self-antigen, not virally infected antigen like this. Okay, so that's CD8 positive T cell activation. Here's kind of like another example of it. So here's a CD8 positive T cell, comes over, MHC class 1 with the self-antigen in it. And then it's going to basically tell this one cell, like, hey, you need to die. But all of these are presenting viral antigen, so it's going to go one by one to kill all of these, and then so forth. Oh, yeah, it's very cool. Very cool, except with if this is a self-antigen. Because we get memory T cells, which we'll talk about later. But that is the issue. Yeah, you would get memory if this was self, so that's why autoimmune diseases exist. So again, CD8 positive T cells, another name for them, cytotoxic T cells. They're releasing what's known as cytotoxins. That's like porphyrin and granzyme. They're not like cytokines. They're like molecules, so they just call them cytotoxin. There's all these other ones here, but I highlighted the main ones I think you should know. IL-2, just because it's cool that it's like stimulating its own growth. Interferon gamma kind of preps that cell to become like, it preps that cell to kind of get ready to be killed, and then it secretes like the killers, porphyrin and granzymes, just like NK cells. NK cells also secrete porphyrin and granzymes. Interferon gamma also plays a role with CD4 positive activation. So it's going to be good to just keep these all kind of straight. Maybe have like a chart and keep them all straight. Okay. So CD4 positive activation is a little, it's the same, but it's a little different because of the cytokine aspect of it. So I kind of put here, what are like the general need to knows? You kind of need to know the role of each T helper cell subtype. Then you need to know what cytokines are differentiating the T sub 0 cell to the TH whatever subtype. Do I want to make a TH1, a TH2, TH17? So you should know what which cytokines are doing that. And then, like if I have a TH1 cell, it's going to secrete its own cytokines. So then you should know that versus a TH2 cell is going to secrete its own cytokines and so forth. And then finally, sometimes they won't say like TH1 positive T cell. They'll just refer to it by its transcription factor. So we're going to talk about that. There's like some good ways to remember them. But you should know that. So then this is the same thing. This is your CD4 positive T cell activation. So here's your T cell, here's your APC. It's presenting MHC class 2, and then it would also have CD4 kind of help. Oh no, CD4 from the T cell helping with that. And then we have co-stimulation right here. It would be 80, 86, B7, what have you, binding to CD28. And then cytokine release. And this is going to tell you the type of CD4 positive T cell. This is kind of like not a thing in the CD8 positive T cell activation. Okay. So this is it again. This is what I'm going to show as my antigen presenting cells. Remember the 3 antigen presenting cells, dendritic cells, macrophages, or B cell. So we kind of did a little bit more yesterday with B cells. That would get kind of confusing to talk about T cell activation. So I'm going to just stick to either dendritic cell or macrophage. So that's what I'm kind of showing here. But keep in mind, B cells are also antigen presenting cells. So the antigen presenting cell has antigen, foreign antigen on an MHC class 2. And then if it's infected, it's going to upregulate CD80, 86, B7. They're all the same thing. This is going to interact with your naive T cell with the T cell receptor and CD4. And then CD28 is going to bind to the co-stimulatory signal. And don't forget, all T cell subtype classes have CD3 on its surface. Okay, so then from here, kind of made this easier because I didn't know how else to make this easier. Here is so we went through signal 1, signal 2. That's great. Now we have signal 3. It could be any one of these could be signal 3. So if it released cytokines that told the T cell to become TH1, it would follow this route. It would follow route A. If it released cytokines to tell it to turn into a TH2, it would follow this route, and then so forth. So TH1, TH2, TH17, a regulatory T cell or a Treg, and then a follicular helper T cell or a TFH T cell. Okay. So my thing with this is try and focus. So there's activating cytokines and then inhibiting cytokines. So this basically means if this APC secretes these guys, it's going to turn into this. Or if it's secreting these guys, it's not going to turn into this. And you'll kind of see what I mean by this. It's kind of confusing, but if this APC is trying to make, like, let's say a TH2, let's say it's trying to make a TH2, it's going to secrete these. So if it's going to secrete these to make a TH2, that's going to be an inhibitor. It's going to be like inhibiting the cell from turning into a TH1. That's why it's like negative. It's like it's inhibiting the process of TH1 because I'm trying to make a TH2. Might not make sense yet. Maybe when we go through these, you'll see what I mean. But I wouldn't memorize these inhibiting cytokines because these inhibitory cytokines are basically the activating cytokines of other T helper cell subtypes. Like, for example, IL-4 is one of the activating ones for a TH2. So it's just kind of going into like, okay, if I really want to make a TH2, I don't want to make a TH1. So something that's going to make a TH1 would be an inhibitory on it making a TH2. Does that make sense, or was that very confusing? I hope you guys know what I mean, but basically focus on these positive ones is what I'm trying to get at, is focus on the activating cytokine. So if the APC is going to give interferon gamma and IL-12, then the T cell it's interacting with is going to upregulate the transcription of the transcription factor T-bet. My dog, he's like breathing very loudly. He just wants attention. It's okay. He's fine. I'm very allergic to dogs, by the way. It's really funny. Okay, but anyway, so this happens here. So signal 3 is going to be giving interferon gamma and IL-12. This naive T cell is going to basically have the transcription factor get upregulated called T-bet. And then from here, we're going to have a Th1 T cell. It looks exactly like, it has all the same features as like a normal T helper cell. You have really no idea that this would be a Th1 subclass unless whatever cytokines it's secreting. And we'll talk about that later. But these are enough cytokines for now. So we have interferon gamma being released and IL-12 that tells this cell to turn into a Th1 cell. If the APC releases IL-2 and IL-4, that's going to that's going to tell this cell to turn into a Th2 cell. And its transcription factor is GATA3, G-A-T-A-3. And interferon gamma inhibits it. Interferon gamma activates Th1, so that makes sense. IL-4 inhibits Th1. IL-4 activates Th2. Okay, so I highlighted what I think is important to know. Because again, they might not tell you this is a Th2 T cell. They might say like there's high transcription levels of GATA3, GATA3. So you're like, okay, that's Th2. All right, how about if it releases TGF beta, IL-1, IL-6? It's going to upregulate something called ROR gamma T. You're going to see it like written like this, ROR gamma T. And then this would be a Th17 cell. Okay, and then if the T cell is releasing TGF beta with IL-2, it's going to upregulate FOXP3. This is probably the most important one to know. I actually have never seen like anyone refer to it as a Treg. It's always like FOXP3 positive. So FOXP3, these are your Tregs. And then lastly, we have IL-6 and IL-21. And if we have IL-6 and IL-21, it's going to upregulate BCL6. So that's kind of nice, maybe a little bit. And that's going to give you your follicular helper T cell, so TFH. Okay. Here's like basically the summary of what we just talked about, and then we're going to talk about the function. So, oh no, we didn't talk about this yet. Sorry, I got ahead of myself. I have a summary slide for you guys, but we're not there yet. So from here, we made a Th1 cell. So this cell got, interferon gamma, this cell got IL-4, and so forth. Now we have a Th1 cell. It's going to secrete its own cytokines, but a lot of the time they're the same as what activated it, which is really nice. Sometimes they're not, and I did highlight the ones that I think are important. All the other ones listed are the ones that are in first aid, but I at least put up the ones that I think are important. So interferon gamma is important, IL-2. These are the exact same ones that activate it, so we're good there. Th2 secretes IL-4, IL-5, IL-13. You should know all three of those, and we'll talk about why you should know all three of those. Th17 secretes IL-17, love that, and then IL-21. Tregs, IL-10, TGF beta, you need to know these, and also these are really important as well, and we'll talk about why. It kind of falls into the role of the Treg. They all kind of go into the roles, that's why it's important to know what they're secreting. And then the follicular helper T cell secretes IL-21. I don't know how important that is, I didn't even highlight it, but we're going to talk about what all of these subtypes do. So if we have a Th1, so why would like the APC want the T cell to turn into a Th1 T cell? And it's when we want macrophages to get activated and if we want to kind of activate CD8 positive T cells. So macrophages are activated, like we kind of meant that like macrophages are differentiated monocytes, but we're going to talk about like when you need macrophages to get really activated. It's a specific type of pathology. We're going to talk about it. You need Th1 cells for that. IL-12. Yes, you're right. I'm sorry. Yeah, it is IL-12. You're right. IL-12 and TGF beta. Oh my God, interferon gamma. Oh my gosh. There's a lot of letters. Yeah, good call. Good call. IL-12 and interferon gamma stimulate Th1, and then from here, the Th1 is going to secrete interferon gamma and IL-2. I think what I meant to say by this was these are the same two cytokines that a CD8 positive T cell is stimulating, or is releasing, which makes sense with the function. Apologies. Okay, so that's Th1. We're going to talk about, again, when you need these activated macrophages, when you absolutely need Th1 subtypes to be activated. Okay, next is Th2. They're releasing IL-4, IL-5, IL-13. These are super, super important for activating eosinophils and increasing IgE for class switching. And I know IgA, that's what 5 is, but mostly for like if we want eosinophils to get activated and if we want IgE. So think your parasitic infections, think allergies. That's where you're going to think about your Th2 subtype. Th17s are weird. So they release IL-17 and IL-21, fine. And what they do is they basically enhance neutrophils. Like they make neutrophils better. I don't really, you don't have to really think about Th7. Neutrophils are fine on their own. It's not like this where like you need Th1 cells to activate macrophages. You don't need Th17 cells to activate neutrophils. It just kind of helps. It like, so when you see a Th17 cell is present, think inflammation. Like it's there because there's some sort of inflammatory process happening. And you'll see like when you next year when you guys go through derm, psoriasis, so like psoriatic arthritis, psoriasis, Th17 is like really, really upregulated. So that's kind of what I'm just think about inflammation with Th17. But it's not like required in any way. Not like Th1 is required to activate macrophages. Tregs, so Tregs are going to come up a lot. These are kind of like, so regulatory T cells, they're kind of like the guys that kind of tone down the immune system. Like, let's say we just had a huge inflammatory response. There's tons of inflammation. But remember, inflammation is supposed to be very acute. You don't want chronic inflammation. This is kind of where you start getting disease states. So one of the mechanisms that the body has in place is to call in more Tregs to the area, secrete IL-10 and TGF-beta, and then that's going to kind of tone down the immune system. It's really, I don't want to say like you're immunosuppressing. It's not like you're suppressing the immune system from doing what it's supposed to do. It's just kind of toning it down. It's like, let's relax. We did our job. Let's chill. So it's trying to it's trying to basically stop inflammation from keep going. It's trying to stop like other ones of these T cells from getting from developing. And again, IL-10, TGF-beta, that will come up in questions. Like these you should associate with like anti-inflammatory, like anti-inflammation, IL-10, TGF-beta. Just say that a bunch of times. IL-10, TGF-beta. These are anti-inflammatory cytokines. And that's why they're secreted by Tregs. And Tregs are trying to like tone down the immune system. And then your follicular helper T cells, these are going to become important. I'm going to talk about these more when we talk about vaccines next week. I keep saying like, oh yeah, vaccines next week, but it kind of ties all of this together. That's why like understanding how vaccines work is really cool because it like ties all of this all together. But these play a really big role in vaccine development. They help to activate B cells. And what they do to activate them is they help them undergo that process of somatic hypermutation and affinity maturation. That's kind of what these follicular helper T cells do. They like live to help the B cell undergo somatic hypermutation. And they are in the follicles. That's where it gets its name. Follicular helper T cell, they live in the follicles. And that's where the B cells are, right? That's your B cell zone. So you can kind of associate those with your B cells. Okay. Here's what we just talked about. Again, there's tons of cytokines. I highlighted on the last one, the ones that I at least think are important. And again, this is cytokines that these cells are secreting. Remember, like this is like a step after the cytokines that turn the naive T cell into that. And then here, it's all their functions, but I wrote under, like if I had to pick like one word or like a phrase to describe its role, Th1, macrophages, Th2, parasites, follicular helper T cells, B cell activation, Th17, neutrophils, inflammation, whatever helps. And then your Tregs is suppression or anti-inflammation, if you don't like suppression. I've come to not like the word suppression. So, like, it's anti-inflammatory. TGF-beta, IL-10. Very anti-inflammatory. Okay. Guys, ready for this? Wow. So this is the big summary slide that I was talking about. And you do need to know this. I'm so sorry. But it really, if you put in the time now to memorize this, I promise it'll make your life easier next year. Like I promise. Because a lot of the times too, they will just refer to like this transcription factor instead of mentioning the actual cell. And then from here, knowing what are the cytokines that are turning this helper T cell into the subtype. And then from here, what are they in turn secreting? So I tried to keep it like color coordinated to like for those visual people out there, like me. But this is, if you know this, you're in good shape. And again, here's kind of like a slide with these exact same things. It's a little bit more condensed, which I like. So this is like cytokines that induce differentiation. These are the ones that we were talking about earlier. These are the ones that are going to be secreted from the APC. The defining transcription factor, this is like another name for a Th1 cell, is like a Tbet positive cell. So that's why it's defining. And then characteristic cytokines, the ones that they release. So these are the characteristic ones that they release. And then their one function. Okay, lots of subtypes. Okay, so I wanted to talk a little bit more about what I mean by activating a macrophage. Macrophages are, on their own, very good. They're very good, right? They phagocytose, they recognize complement, they have complement receptors, they have Fc gamma receptors for antibodies, they have their antigen-presenting cells, they can activate all sorts of stuff. They can do all sorts of stuff. But if you have a mycobacterium infection, which is what they're showing here, mycobacterium, so like tuberculosis, that's not how you spell mycobacteria. So TB. Mycobacteria is an intracellular bacteria. And this is, again, you'll do this summer, but bacteria, remember, bacteria aren't supposed to be intracellular. Bacteria are exogenous, right? That's why they're usually processed by MHC class 2. Intracellular. There's a subset of bacteria that live within macrophages. And it's just probably like an evolutionary thing. Like they're like, oh, like, let me just survive in the cell that's trying to kill me and then I'll live forever type of thing. So it probably evolved to do that. Mycobacterium is one of them. There's some other ones like chlamydia. Chlamydia like lives lives within cells, but it's a weird thing that certain bacteria that are intracellular do. Okay. But when we're talking about Th1, I really want you to think about macrophages against mycobacteria. And there is an immunodeficiency with this and we'll talk about that. But basically, let's say, here's mycobacteria. It's really good at living within macrophages. So the macrophage engulfed it, and now it can't kill it. It's like having a really difficult time trying to kill that. So what it's going to do, it's an antigen-presenting cell, right? So it's going to be like, shoot, I can't do it. I need help. I need a Th1 cell. So what it's going to do is it's going to go find a naive T cell. It's going to activate it, and then it's going to tell it to turn into a Th1 cell. Th1s secrete interferon gamma, right? So Th1s secrete interferon gamma, which is right here. And I put also CD40 ligand because this is like the immunodeficiency. Like if you don't have CD40, we're going to talk about that like later. But this is the big guy with mycobacteria. You need interferon gamma. Once interferon gamma gets released, the macrophage has interferon gamma receptor. What receptor doesn't macrophage have, right? They have every single receptor. And what this does is it basically just makes the macrophage better. Like an activated macrophage is just a more efficient macrophage. It's just better. So like more efficient phagosome-lysosome fusion. Remember when like it ingests something, the lysosomes come in and like fuse with it and then like they can digest. Mycobacteria, for example, can actually stop that process from happening. They have like ways to kind of stop the lysosomes fusing with the phagosomes. But if it activates a Th1 cell and Th1 cell secretes interferon gamma, now it's like it can overpower like the mycobacterium trying to stop fusion. So the lysosomes are going to fuse with the endosomes or the phagosomes. Remember, it's like the same. And you can get more proteases released. You can just get more things in this macrophage that can help it kill this mycobacteria. And again, this is why I want you to think of mycobacteria with this process, because it is this is required to basically kill any mycobacterium species. I know I mentioned mycobacterium tuberculosis, like so TB, but if you see a random mycobacterium species, you still need Th1 cells. Okay, so then, oh yeah, okay. Does that make sense? So you're activating macrophages, meaning you're making them better. Okay. And then I wanted to show you briefly like what these follicular helper T cells do. Again, we're going to talk about this with vaccines next week. But we're in the follicle. So we're in the follicle of some, organ, some secondary lymphoid organ. So the follicular helper T cell basically is going to show, like, it's going to basically make this B cell, so remember somatic hypermutation and whatnot. So when it's kind of going through this process of activation, you kind of need this T follicular follicular helper T cell to activate the B cell. So remember yesterday when I was like, oh, this is like a T cell it's an already active T cell that's activating this B cell. It's more likely than not going to be a follicular helper T cell that's activating the B cell. So if you want to go back to yesterday's notes, right, and go back to the slide where I show, oh, here's signal 1, here's signal 2, and I have this is like a T cell. It could be just any T cell, it really can be, but if it's like the follicular helper T cell, its entire role is to help the B cell get activated. So that's why the follicular helper T cell has CD40 ligand on its surface, so it can bind with the CD40 for signal 2. Here's signal 2 for B cell activation. Here's signal 1, and then here's signal 3, which isn't a real signal, but... So super important for your T-dependent B cell activation. Okay, so that's your follicular helper T cell. And then T regulatory cells, let's say we have a deficiency of T regulatory cells in general, or let's say the T cells, there's an issue with this transcription factor, like the gene coding for this transcription factor, so FOXP3. If that's going to basically disrupt this balance, and then you're going to have it's going to tip to the side of having more autoimmune diseases. So you're going to have less Tregs and more of the other T cells. And again, whenever you don't have this balance in the immune system, you're at risk for developing autoimmune diseases. So you don't have to know this chart. I was just kind of showing you can think of it as a balance. The Tregs are there to kind of balance everything. If we have inflammation, the Tregs try and tone it down. If we have too much T cells, the Tregs try and balance those out. So if we have something happening where they're deficient or FOXP3 levels go down or the gene is messed up, you're not going to have enough Tregs, and then you're going to have the scale's going to tip, and you might have an increased propensity of developing autoimmunity. So one example of this is called IPEX syndrome. So IPEX stands for immune dysregulation, polyendocrinopathy. Great, just like error mutations, right? Enteropathy, and it's X-linked. So a lot of the times, so yes, this is very similar to your APS, and so the autoimmune polyendocrine syndrome. It's very similar to that, but they're going to kind of give it away in some way. They're going to have to tell you something about FOXP3. So I don't know if this is much of a buzzword B type of thing, but I just put this on here because this is a genetic disease of this transcription factor. So we do not have this transcription factor. So now we're going to have decreased Tregs, and that's why we get autoimmunity, because the scale is going to tip in that direction. So we're going to get more autoimmune diseases, and one of the classic ones that we get is IPEX syndrome. It's X-linked, so it's only in males. It's only ever going to be in males. And an important thing to note is if you have type 1 diabetes, usually you don't have type 1 diabetes in an infant. A very young child usually doesn't have type 1 diabetes. So that's it. Not really a buzzword situation, but it's oh, maybe I should be thinking about one of these immune, autoimmune issues. So this is IPEX. It's going to be pretty similar again to the autoimmune polyendocrine syndrome, but there's going to be little things in there where it's going to lead you to know, okay, maybe even in the prompt it'll say the gene coding for FOXP3 is non-functional. You're okay, this is IPEX. And no, you don't have to know. No, you don't have to memorize. Just an example of polyendocrine. Just many endocrine stuff. But also immune dysregulation. So there's still going to be other issues too, asthma maybe, random immune disorders and stuff. So, okay. So what happens if the T cell receives signal 1 without co-stimulation? So signal 1 without signal 2, this is exactly like B cell. This is peripheral tolerance. This is anergy. So if you have signal 1 without signal 2, clearly that's a bad T cell. That was a T cell that escaped central tolerance. And so that's why we have peripheral tolerance, to kind of catch these types of cells. So that's going to become an anergic T cell. And remember, anergy is just like inactivation. And again, I don't know why it doesn't just die. I really have no idea. There's no receptor editing that happens here. It's not like B cell like selection processes. It's just straight up the T cell reacts, gets signal 1 without signal 2, it becomes anergic. So even if you stimulate it with another antigen, even if you give it signal 2 after the fact, doesn't matter. It is anergic. It cannot be bothered. And then eventually it'll die. But this is like peripheral tolerance, as we kind of mentioned. And this is kind of what I just talked about. So let's say here's your normal specific antigen and co-stimulator. So we have signal 1 and signal 2. This is signal 1 without signal 2, anergic. And then this is, even if we give it co-stimulation after it's become anergic, doesn't matter. It's going to stay anergic. An anergic T cell, for all intents and purposes, is a dead T cell. It's just kind of floating around. It can't react to anything. It can't do anything. It can never get activated again. Okay. You guys have any questions? It's a lot of subtypes of T cells. I don't think I missed anything in the chat. No, okay. Are you guys ready for some questions? Okay. Okay, it's about time. Okay. So this basically, long thing, all it's really saying is we have a double positive. We have a double positive T cell. So clearly this is an immature T cell. This is a type of cancer. You don't have to know that this is a type of cancer, but a lot of the times cancers are immature cells. So this is a double positive T cell. Where are those found? Those are found in the cortex. So some of you guys with medulla, remember that it undergoes positive selection in the cortex and then negative selection in the medulla. Maybe that's where you're thinking about the positivity, but when it's right before it even goes through that process, it generates the double positivity is generated after the beta chain is, the surrogate alpha chain is added to the beta chain. It's allowed to proliferate. That's in the cortex still. And then when it's still in the cortex, it undergoes that positive selection and then it moves to the negative selection, which is when you get the single positivity. Make sense? And this is kind of, yeah. Does that make sense? Go back to that slide. Actually, we can do it right now. We have some time. So that, like I said, I really like this slide. I just think it has like everything on it that you need like to know. And that's kind of where your double positive cells are still up in this cortex. They're still up here. Technically, yeah, the double negative ones are too, because they're kind of coming from the bone marrow. They have to get to the cortex. So technically, so are the double negatives, but they're both in the cortex. And then we have positive selection up here and then negative selection down here. So again, generate TCR. This is your double positive, well, double negative first, and then double positive. And then we go through positive negative selection, and then we get to our single positive before it leaves. Okay. Okay, next. Okay, you guys ready to go over this one? Okay, so some of you didn't got here, which is good. TNF beta is not TGF beta. We didn't talk about TNF beta. So these are kind of the ones to look at. But regardless, you still could have answered this regardless, because we got mycobacterium. And remember, what is the cell that you always, 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 always need in mycobacterium to activate the macrophage and make it better? And it does this by secreting these cytokines. It's going to be your Th1. Okay, so if you picked macrophage for this, I get why. It's just, if you read, it's just kind of like like you just probably read it too fast. You're like, oh, but like the pattern of cytokine production. So like what's secreting these cytokines? That would be the Th1 cell. It makes the macrophage better at killing any type of mycobacterium. Okay, and then here's kind of like what he says here. You really don't need to know about TNF beta. I've really never seen anything about TNF beta anywhere. Okay. Okay. Oh, yeah. Yeah, so TCR is T cell receptor. Mm-hmm. Okay, so that was a minute and a half. I really like this question. I think this is a really good question to see if you understand T cell development. And again, we just learned it, so it's okay if it's not there yet. You guys are a little all over the place. Totally fine. Totally fine. So basically what they're asking is when the T cell comes from the bone marrow and it first enters the thymus, it's first entering. Remember, it's going to be double negative. So remember, it's not going to have CD4 or CD8 on its surface. As soon as it enters, it's double negative. It doesn't even have CD3 on its surface. Like, it has nothing on its surface when it enters. And then when it's there, then it becomes, it's going to be double negative. Beta chain's going to rearrange. It's going to brace gamma delta. We get our surrogate light chain, our surrogate alpha chain. So PT alpha gets added to it, proliferates. Now we get double positive T cells. So this is going to be a little bit after, this double positivity is going to be a little bit after they first enter. And then once we get alpha chain rearrangement, that's when we have a positive T cell receptor. So when it's first entering, it has nothing. It's CD4 negative, CD8 negative, and it has no T cell receptor on its surface. We need to make it. That's the whole point of like going into the thymus, right? So here's kind of like, this is why I liked this picture from first aid. It kind of shows all of this stuff. Like when it's leaving the bone marrow, and I think it's a little misleading here because you're like, oh, well, it's showing in the cortex. But when it first gets there, remember, it doesn't have anything. It needs to go through that whole process. I'm going to do it. I'm going to go all the way back to my favorite slide. It's coming in. It first comes in. Here's your double negative T cell. We have to make the receptor. And once we have like this race for rearrangement here, this is when we have mature. And remember I said mature means that there is the presence of the T cell receptor. So it comes in, it goes to the cortex, it's double negative. We're going to make the receptor. Then like when this proliferates, this is your signal to become double positive. So I can see why some of you guys did pick double positive. They are double positive, but it's just like not right away, if that makes sense. And then from here, then they turn into your single. Then they go through positive and negative selection. That's when you get your single positive. So kind of like back here, this is kind of like the way that it happens. So we make it with double positive cells, then we're testing it, and then we get our single positive cells. Okay. Make sense? I know these are hard. These are hard. I did not go easy on you guys. So they have the T cell receptor when they enter thymus. It gets made with double positive. Yeah. So again, it's like the T cell receptor, when the T cell receptor is like made, is like after that alpha chain rearrangement. So I should have really just put this slide like just everywhere. So we're gonna get rid of the red. This is like when it gets the T cell receptor, like it has the full T cell receptor. So this is like the T cell receptor rearranging beta. You put on the surrogate alpha chain. This proliferates, again, just like B cell receptor development. When you have the heavy chain with the surrogate light chain, that proliferates. This is proliferating. This is your signal to turn into double positive cells. This is like your signal. Like the beta chain with a surrogate alpha chain proliferating tells these T cells, like, okay, put CD8, CD4 on the surface. Like, go ahead and do that. It does that, becomes double positive. Now the alpha chains get rearranged. And then at the end of the day, now we have a mature, meaning T cell receptor is there, double positive cell. Now it goes through positive selection, negative selection. That's why positive selection still happens up here in the cortex. And then when it's done, it undergoes negative selection down in the medulla. That's when it becomes either single positive CD4 or single positive CD8. Okay, any other questions about that? Again, I tried to like put on here questions that I thought that you could genuinely get asked, so. Okay. I was nice and I even gave you what organ this is. Actually, I don't know if it told you that. No, it doesn't tell you that. Okay, that was about a minute and a half. Anyone wants to answer before we discuss? Okay, so this one. I told you it was the thymus. If I didn't tell you it was the thymus, you could still get it. Anterior mediastinal mass. Remember I said that's like the location of the thymus, an anterior mediastinal mass. Well, sorry, an anterior mediastinum. So this is a thymus. So with this process, this arrow is pointing to the medulla. So the cortex is out here, the medulla is in here. Remember, here's your well, I covered all of them. But here's your Hassel's corpuscles in here. So we know that this must be the medulla. I know it's really tiny, but that's your medulla. So this is going to be negative selection. Remember, positive selection is in your cortex. Some of you guys picked thymocyte formation. Not a bad thought, except this is a 40-year-old man. So remember, the thymus involutes by the age of 3. So if this said like a 1-year-old or a 2-year-old, they probably wouldn't have this as an answer because like it would be, well, they wouldn't have both of the right answers here. But since this is a 40-year-old man, this is actually like, this is not a true thymus. This is like a cancerous thymus. Like this is cancerous thymus. It's okay. It's all right. So positive selection out here, negative selection in here. Look for Hassel's. What does he have? He probably has like a lymphoma, like some sort of lymphoma or leukemia or something. Sometimes what can happen is the thymus like can become like, so the thymus involutes. It's not like it just disintegrates. It's still there. It's just not functional. It like that's what involuting. I guess I could have went over that a little bit better, but it like kind of just like folds in on itself. So it's still there. So it's not really common, but it can pick up, like it can start replicating again. But when it does, it becomes cancerous more likely than not. So he probably has, actually, let's see if it says what kind of cancer he has. It does not. Okay, so he probably has like one of those, like just one of those leukemias or lymphomas in which it's like the self-react, like the T cells, like a T cell like a T cell or a B cell, like lymphoma, which is a cancer of the lymphocytes. Not 100%, I didn't put that on here. Does that make sense? So again, look for Hassel's corpuscles. You know you're in the medulla. That's going to be your negative selection. Okay. Okay, that was 90. You guys are like 50-50 on this. I love it. I love it because you won't get it wrong on the test. You're 50-50 on one of them is right. Okay, so this one, some of you guys did get gut. It's okay. We're gonna talk about why. So basically, this one they're saying, okay, They're looking at T cells in response to tumor cells. So a T cell in response to a tumor cell because the tumor cells lack the necessary co-stimulatory molecules for lymphocyte activation. So it's basically saying tumor cell, T cell. The T cell is going to have like T cell receptor, TCR, and then it's going to have its co-stimulatory signal, right, which is CD28. Whatever is kind of like it's trying to attack, it needs to still get signal 2 to get activated. So let's say this is your tumor cell, this is a melanoma cell. It's going to have self-antigen, or not self-antigen, sorry. It's going to have like some sort of antigen, and it's also going to have its co-stimulatory signal. They're saying here, this is lacking the co-stimulatory signal. It's lacking it. So it's not properly, this T cell is not properly getting activated. So what would you transfect to make this seen by the T cell B7? Does that make sense? It was a little confusing because like a melanoma cell is not an antigen presenting cell, but that's kind of the idea. It didn't specify that this was like a CD4 T cell or CD8. This could have well be like a CD8 positive T cell. Transfect means to like add. So if I'm going to transfect B7 to this system, I'm going to add it to this system, basically. So if the melanoma cell, you were trying to make this cell express B7. That was a tough one. These are all tough. I promise. These are like, if you're getting all of these right now, then you've definitely had some immuno background or something, because like this is a lot that we've been covering. But does that kind of make sense? So like if you picked CD28, totally get it. That's like, I'm glad you didn't go for one of these other guys. But that's what they're asking. They're saying like, which of the following would be the best candidate for the tumor cells? Like basically, what do we want to put on the tumor cells? Because the tumor cells are lacking the necessary co-stimulatory molecule. So what would be the best co-stimulatory molecule to kind of add to this? It'd be B7. What could have been written here instead of B7? Do you guys remember? Just something to keep an eye out for. Yes, good. Yep. CD80, 86. It would be written just like this, CD80-86. Good. So that's the same thing. So if it says CD80, 86, that would also have been correct here. Okay, cool. Good. Cool. Yeah. So that's kind of what they're saying. They're like, let's induce the tumor cell to have this co-stimulatory molecule on it so that the T cell would think that it's getting signal 2. It's going to get activated. It's kind of like pretending like this tumor cell is an APC. But that did make the question a little confusing. I agree with transfection, but you're trying to mimic that signal 1, signal 2 reaction so that the T cell is like, okay, I see the cancer cell. So there's this question and then 2 more. Okay, 90 seconds. All right. So, 2-year-old boy, blah, blah, blah. Okay. Mycobacterium fortuitum, Mycobacterium smegmatis, Mycobacterium blah, blah, blah. Okay. Mycobacterium. And remember I said it could be any Mycobacterium infection. What do you absolutely, absolutely need to get rid of a Mycobacterium infection? Is TH1. Good. What does TH1 secrete? Why do you absolutely need TH1 to get rid of it? And it's because it secretes interferon gamma. So this, fun fact, is actually an immunodeficiency we're going to talk about next week in the immunodeficiencies. It's actually, if you have a lack of interferon gamma receptors, you can't fight off mycobacterium infections. And this is why the TH1 cells are fine, but they can't, like, all their interferon gamma they're secreting isn't helping the macrophage be better killers. So you can't. Immuno is not scary. Immuno is cool. No, I'm kidding. It is scary. I know. Any of these things go wrong, you're like, wow. Encapsulated. So mycobacterium is actually, yeah, so it's not encapsulated. What are you thinking of? Maybe you're thinking of Neisseria? Meningitis, maybe. Mycobacterium actually has a really weird structure. It actually isn't. Remember, we kind of talked about like, oh, here's peptidoglycan and then LPS and gram negative, gram positive. Mycobacterium actually doesn't even have peptidoglycan. It doesn't have LPS. It has an entirely different cell wall. And this is like something you'll learn this summer with micro, but you can't even do a gram stain on mycobacterium because it doesn't have peptidoglycan. It doesn't have the normal bacterial cell wall. You have to do a certain type of stain called the acid fast stain. So if you've ever been doing questions and you see like you see an acid fast bacillus or an acid fast bacteria, they're talking about mycobacterium because it has a really weird cell wall that it only gets stained with what's known as an acid fast stain. There's your little fun fact for micro that you can look forward to. But yeah, so it's not encapsulated, it has a totally different cell wall makeup. So yeah, don't think about like capsules with mycobacterium. Okay. So there's this. Anything I wanted to say here? Yeah, so key point. I always like to look at the key points. Child, recurrent atypical mycobacterial infections. Okay, but even TB, if he had TB again and again, should bring to mind macrophages, TH1 cells, IL-12, interferon gamma. And again, I think interferon gamma receptors were like emphasized in this question because this is a type of immunodeficiency. It's literally called interferon gamma receptor deficiency, and it's just recurrent mycobacterial infections. Okay. All right, 2 more. Got that a little too fast. Yeah, you wish it's all the answers, right? Okay, that was 90 seconds. Okay, let's talk about this. So Yes, they give you the drug. We did talk about this drug. It's okay. You could have gotten it without it, though. It tells you what the drug does. So this is saying this drug binds a specific T cell receptor that is upregulated in many cancers and negatively affects immune regulation of malignant cells. Cool. Inhibition of this receptor simultaneously blocks co-inhibitory signaling of T cells and promotes CD28 co-stimulation, thereby reversing the negative immune regulation. So I agree, the wording of this is kind of confusing, but this is basically saying we have a T cell. We're going to talk about the co-stimulatory signals. So it has CD28 on its surface. Nope, 28 on its surface. And then like the cancer cell, cancer, okay, T. Its co-stimulatory signal we know is B7. Well, normal, co-stimulatory signals are B7. But this is saying that, remember what we talked about? This checkpoint inhibitor binds a specific T cell receptor that is upregulated in many cancers and negatively affects blah, blah, blah. So what can happen is they can actually upregulate, these cancer cells can trick these T cells into upregulating a blocker of B7. Guys, remember what that one was? But it's basically like this cancer cell is like, no, like you should upregulate this. And that's what it's saying. It binds a specific T cell receptor that is upregulated in many cancers. So this gets upregulated. This mysterious compound gets upregulated. It blocks the co-stimulatory signal. So now this T cell can basically never get activated. So they make this drug which blocks this blocker. It's very confusing. Blocks this blocker so that we allow for B7 and CD28 binding. CTLA4. Okay? So draw it out. 28 normally binds to B7. Yes, you did get got. Very good. Yes. But see, you get got now, you won't get got in the exams, which is all I care about. I actually love when you guys get these questions wrong because I'm trying to get you. I really am trying to get you. Some of them I'm like, I'm not. I'm trying to be like, look, you learned. But some of them I'm like genuinely trying to get you so that you won't do this on the test. So I am picking like harder questions. But this is what CTLA4 does. And it's on the T cell. Maybe that's where some of you guys might have gotten confused. Go back to that. I know we only briefly talked about it today, but kind of go back and look at that image from Amboss. I think it's a really good image. It even shows you ipilimumab. Like it even shows it to you. But this is what CTLA4 does. And it can be induced. Like I know I said that this was a cancer cell. This could have also just been an APC. It doesn't matter. You won't get stimulation of this T cell if CTLA4 is up. So CTLA4 is up. It blocks B7. So that will never get activation of this T cell. This T cell will only usually get, if anything, it'll just get signal 1 energy. So that's why ipilimumab is so cool. It binds to CTLA4. It brings it out of the way so that now this T cell can actually bind to B7 and it can go find the cancer and it can go kill the cancer. But I agree, this was asked kind of weird, but I did want to show you like they are at, like, again, my friend had this on her boards. I wanted you to see like a question about it, like how they can maybe ask it. I know you guys aren't taking boards, but not yet, but still. That's kind of what it's saying here. Okay. Good, and then last question. Nice little review, right? Okay, that was 90. Let's talk about it and I'll answer like the questions you guys are asking me to in the chat. So I'm going to explain what this question, I think some of you guys are confused on what it's asking. So let me explain it. You can re-answer if you want. But this is basically, you don't even need all of this. This is all just basically saying this guy is producing tons of IgM antibodies against the capsule of strep pneumonia. So it's saying, like, again, you could have just read this, the effector mechanism most likely to act in concert with this early IgM production to clear infection is. It's basically just asking why is the body even producing IgM? If we know it's a weak mechanism, it's IgM, so it really can't do many things, but why do we still like getting IgM produced? That's kind of what this question is asking. So like the effector mechanism, the mechanism behind like basically this early IgM production, the effector mechanism of it is to do what? Did I explain that better? Maybe I didn't. Maybe I made it worse. But that's kind of what this is getting at. It's kind of like something that we emphasized yesterday, talking about how this is the whole point of why we like to still make IgM, even though it's not specific for the capsule. We need to see a protein in order to get IgG. Okay, so this one is going to be complement-mediated opsonization. I do think they worded this kind of weirdly. IgM is not an opsonizer. We talked about this, but you're still... So with IgM, we get complement. So then when we get complement activation, we make C3b. And that's your opsonizer. Nope, C3b. So that's what this is saying. Like, the effector mechanism with this early IgM production is to get complement and to get the C3b. It's a confusing question, but regardless, ADCC, IgM does not in any way downstream produce ADCC. Remember, it's only IgG can do this with NK cells, or IgE can do this with eosinophils. Cytotoxic T cells, IgM has like really nothing to do with cytotoxic T cells. If this was a helper T cell, I could see why that would be like maybe a little bit more appealing of an answer. Because like you would need that for maybe eventual helper T cell, like for eventual like class switching. But cytotoxic T cells are really not involved with like bacteria, and especially not when you're already producing IgM. LAK cells, no clue what those are. We'll have to go look at the answers. I don't know what those are, unless it's a weird name. NK cells are pretty much like the CD8 positive T cells of the innate immune system. They really work on viruses and they work on like cancer cells. Anything that's going to downregulate MHC class 1, which is what viruses and cancer cells tend to do. That's where NK cells kind of act. But again, they don't really need antibodies to do that. If anything, they need IgG to help with ADCC. But I know that this was kind of weird with this opsonization, but I think what they're getting at is C3b. Like, I think they're getting at, like, we have early IgM production. I really, again, want you to kind of, like, associate early IgM production, which is, like, really weak, nonspecific, kind of, like, not a great, it's a T-independent, like, antibody response. I just want you to think complement. Like, that is really the only reason we're producing this. And if we get complement activation, we're going to get C3b, so at least we're going to get opsonization. Like, at least we'll get some opsonization out of it. But I agree, it was kind of written weirdly. Like, you're like, wait, but IgM's not an opsonizer. It's not. It itself is not acting as an opsonizer, but it's activating complement, and then we're going to get complement-mediated opsonization with C3b. Oh yeah, ADCC is antibody-dependent cellular cytotoxicity. So I think it's easiest to explain with worms because they're really big. So here's a worm. We have IgE, which is going to bind to it. So remember, the FAB portions of IgE binds to the worm. The FC portion is sticking out, so this would be like FC epsilon. It's like sticking out. Eosinophils have FC epsilon receptors on them, so here's an eosinophil. It has the receptor for the FC portion of epsilon, so FC epsilon receptor. That's what it has, so it comes over here. It binds to the FC portion of this IgE antibody. And then once it does this, I'm not showing the cross-linking, but you'll get cross-linking. And then once this happens, these can release mediators, which is going to basically destroy the worm. So it's like antibody-dependent cellular cytotoxicity. Cellular cytotoxicity, you're destroying, like you're releasing compounds that are going to destroy something. Antibody-dependent, because it's like this antibody is drawing these cells into the area. It works with NK cells too. Let's say we have a let's say we have like a viral infected cell. So it goes like this. And then let's say like we have IgG that binds to it or something. Oh, maybe it's a bacteria. Let's say this is a bacteria. Okay, this is a bacteria. And we have some IgG sticking to it. Remember, IgG can be an opsonizer, so it can kind of even just bind to this, trying to neutralize it. Or it can just bind to it in this way, and then it's going to call over NK cells. NK cells have Fc gamma receptors. Fc gamma receptor. This is the Fc portion of IgG, so this would be called Fc gamma. So NK cell comes in, and it binds all along here, and then it can destroy this. So again, antibody-dependent cellular cytotoxicity. We're destroying this cell. So basically they wanted to know what happens after you release IgM. Yeah, I do still think that this is worded weirdly. Like if this just said complement activation, I think that would have been a lot better. But I think what they're trying to get at is like early IgM production is still beneficial because you're going to get opsonization out of it because of complement. IgM itself is not an opsonizer, but after you go through the complement pathway, you're going to get opsonization with C3b. Is that what it's saying? Yeah, C3b. So that is kind of what it's referencing. You're welcome. I'm really curious what LAK cells are. Lymphokine activated killer cells. NK cells that have been stimulated in vitro. Oh, please. You do not have to know what these are. I've never heard of that. And I work in vitro, right? I work in a lab, but please. LAK cells. All right, so does that make sense? This is kind of like weird question, but just kind of wanted to bring in some stuff from yesterday because it had some answers in it with T cell stuff. So just kind of wanted to show you like more overall immuno. We're going to start getting more and more overall immuno questions, which is good. Guys are going to be immuno masters. Okay. That was it. I actually finished on time. Yay. All right, let me stop recording.